Right, so hi everybody. Today what we're doing is a lab on interference. So before we get into the experiment, what I'd like to do is just recap some of the important concepts that we talked about in lecture. So first thing is, what is light? As we saw, light is something a bit mysterious and hard to wrap your head around in a lot of ways because in some cases it appears to behave like a particle, and in other cases it appears to behave like a wave, and this is called the wave-particle duality of light. We don't really need to go down that road right now. For this lab, we're only interested in ways that light behaves like a wave. So in particular, we can think of light as an electromagnetic wave, right? Now, one property that all waves share is the property of superposition. And this means if you have two waves that meet at the same point in space, you can simply add the two waves together to get the combined effect of those two waves. It's pretty simple. And that leads us directly to the idea of constructive interference and destructive interference. So constructive interference occurs when the two peaks of the two waves overlap with each other, giving you an even larger peak, a more intense wave than what you had before. Destructive interference occurs when the trough of one wave meets with the peak of another wave, and they effectively cancel each other out, giving you zero intensity as a result. Okay? So in today's lab, our light source is going to be a laser beam, and we're going to send that laser beam through two narrow slits. Okay, so this apparatus you see here has a bunch of different slits on it, but when we send the light through two narrow slits, effectively each slit is now going to be a source of light. Now those two different light beams coming through the two different slits are going to combine later on, and sometimes they'll combine destructively, and that's when you're going to see a dark spot. Other times they're going to combine constructively, and that's when you're going to see a bright spot. So the pattern of light and dark spots that occur when you send a laser beam through the two slits is called an interference pattern. And so we're going to look at the properties of interference patterns in today's lab. Okay, now let's take a look at the experimental setup here. First, we have a track with various pieces of equipment mounted on it. And if we start from the far right side, what we have is a laser. Now, the wavelength of the light emitted by this laser is 635 nanometers. So that's going to be constant throughout the experiment. The wavelength is 635 nanometers. The next thing that we see as we go to the left is the slit assembly. So the slit assembly just has various pairs of slits. We can change the distance between them. Right now, the distance between the two slits here is 0.5 millimeters. All right, so if we work our way down the track, on the far left side, what we have is the light sensor. So what this does is it measures the intensity of the light that's going through its aperture, and we can actually measure or read out those measurements of intensity using our computer interface. So that's what we'll be doing. But notice that not only can we measure the intensity, but we can also change the position of the light sensor. So in other words, we can see how the intensity of light depends on the position of the sensor. One thing we should note is that on the track, the light sensor is at 20 centimeters, and the slit assembly is at 95 centimeters. So the distance between them, again between the slit assembly and the light sensor, is 75 centimeters. So that's something you'll need to record. Okay, and now I've cut the room lights down so you can really see the interference pattern a lot more clearly. This is what it looks like when we take that laser beam, we send it through two slits, and then we project it onto a screen. You see the interference pattern. It's this pattern of bright and dark spots that you see here. Where you see a bright spot, we know there's constructive interference going on. When you see a dark spot, you know there's destructive interference. So the way the experiment is going to work is we're going to take our light sensor, and we're going to start it all the way at one end, and then we're going to start collecting data And while the data is being collected, we're going to just slowly push the light sensor to the other end. So basically, we're going to sweep across the entire interference pattern so we can see how intensity changes with position within that interference pattern. Okay, now let's take a look at the data when we plot it all out. So what you're seeing here is a graph of intensity versus position. So intensity is shown on the vertical axis right here. That's what the sensor is picking up as the light intensity. And the position of the sensor is shown on the horizontal axis right here. And you can clearly see the interference pattern where we have alternating regions of high and low intensity. Wherever the intensity peaks, we call that an interference maximum. And wherever the intensity is at a low point, we call that an interference minimum. You can also notice that there's a center of the pattern where the intensity is the largest, and that's right here. So what we're about to do is measure the distance between different peaks in this interference pattern. So in particular, the first thing we're going to measure is what is the distance between the center of the pattern and then the n equals 1 interference maximum. Okay, so the way we can measure this is to click on that central or n equals 0 maximum, and then just drag the cursor over to the first peak to the right of that, and the distance there is 0.92 millimeters. Okay, so 0.92 millimeters between n equals 0 and n equals 1. Next, we can measure the distance to the second maximum from the center. So again, start at the central maximum, and then drag over to the n equals 2 maximum. And now the distance is 1.91 millimeters. Do the same thing for n equals 3. Okay. Now that distance is 2.86 millimeters. Do the same thing for n equals 4. Now that distance is 3.74 millimeters. And then finally, we'll do n equals 5. There's the fifth maximum down here. That distance is 4.74 millimeters. So in this one measurement, we were able to find the distance from the center to all of these different n values of the maximum. Okay. Next, I've changed the slits so that now the spacing between them is 0.25 millimeters. And now we have a slightly different type of interference pattern that you can see here. So we'll do the same thing with it. We're going to start with the sensor at one end and then slowly push it towards the other end, all the while collecting data of the intensity. So we're sweeping across the interference pattern once again. Okay. So let's take a look at the interference pattern when we plot it out on an intensity versus position graph. So again, this is for the 0.25 millimeter slit separation. What we're interested in is what is the distance between the different peaks in this interference pattern. So we'll start by identifying the center of the pattern. That's again the highest peak in intensity. This is n equals 0 right here. So if we start there and then drag to the n equals 1 peak in intensity. Let's try that again. We can measure the distance between them, which is 1.90 millimeters. Okay, so if we again start at the center and then drag to the n equals 2 peak of intensity, the distance here is 3.88 millimeters. We do the same thing for n equals 3. Distance is 5.79 millimeters. Okay, let's do the same thing for n equals 4. Distance between that and the central peak is 7.71 millimeters. Then finally we'll do it for n equals 5. That distance is 9.62 millimeters. All right, so that's it for the experiment. what you'll then be doing if you follow along with the worksheet that accompanies this video and some of the analysis that's done there, we'll be looking at a comparison between the experiment we just did and some of the theoretical equations that we developed in lecture. So in particular, I want to remind you of the equation d sine theta is equal to m times lambda. Now, this equation describes in a double slit interference pattern where you would expect to see the peaks or the highest intensities. Now, if you compare that equation to the results of our experiment here, you should find very, very close agreement. So if you do the calculations and you're finding that there's wild disagreement, double check what you did, because there should be very close agreement. Now that's it for today. I'll see you in the next lab video, but until then, please be safe and healthy out there. Take care.